So remember what we were talking about. We're talking about Cauchy sequences, right? Cauchy sequences. Okay. Turn to your neighbor and tell them what a Cauchy sequence is. Remind them what it is. Yeah, either roughly speaking, so intuitively, or precisely. You can either read off the definition to them.
They keep getting closer, not closer to something.
That's how it's different from
Okay, so remember we had two ways of thinking about it, right? One was that you look at the diameter of the tail, right? The diameter of the tail, and the limit of the diameters of the tails goes to 0 as n goes to infinity, right? As you let the start of the tail head off towards infinity, the diameter of that tail heads to 0. Okay. More precisely, or not more precisely, but maybe more formally, you say that G sub n is Cauchy if for all epsilon there exists an n such that if you have any 2 points past that time, then the distance between those 2 points is smaller than epsilon. Right? So the distance between, you can control the distance between any two points. Right? So that was one definition, and we had this other definition of complete, which meant that complete metric space, which meant that Cauchy implied convergent. Right? Any Cauchy sequence was a convergent sequence. Right? The opposite was always true. If you're convergent, then you're always Cauchy. But if it's complete, then that means that these are equivalent to each other. That Cauchiness and completeness, convergence are the same. Okay, and we had finished up with this theorem that says X, a compact metric space, implies that X is complete. Right? Any compact metric space is complete, and there's a second part of the theorem that says that any Euclidean space is complete. Okay. Yeah.
When we were talking about sets, didn't we have a definition for completeness? Like it contains all its limit points or something like that?
No, you think of perfect, I think.
Okay.
Right? Yeah, that's different. Yeah. Yeah, perfect meant that every point was a limit point.
Okay.
Yeah. No.
Like we would say, wouldn't we say that R is complete or something?
No, we haven't used this. I'm pretty sure we haven't used this adjective yet. We had closed. We had perfect, but not. I'm pretty sure not complete. Okay. So so let's prove. We proved A last time, and let's prove B. Proof of B. So why would RK be complete? So all we need to do is to show that it suffices to show that any Cauchy sequence is bounded. Right. Suffices to show that any Cauchy sequence is bounded. Right? Because if your sequence is bounded, then it lives in some bounded set, right? You take the closure of that set, then your sequence is sitting inside of a compact set, a compact metric space, right? And so you would have by part A, then you know that your sequence converges within that space. Hey, Lara.
Can sequences be compact?
We talk about sets being compact, but you don't talk about a sequence being compact. You could talk about maybe the image of a sequence being compact, right? The image of the sequence, but not, Okay. That's like saying that the function is compact. Well, the function isn't compact. You could talk about the image of a function being compact. Okay, so suffice it to show that any Cauchy sequence is bounded, right? Because once you do that, you're living inside of a compact set, right? Because remember in RK, in Euclidean space, as long as it's closed and bounded, it's compact, right? So if you're living inside a bounded set, just close it, you're living inside a compact set, right? And then we're in case 1, and so your Cauchy will imply convergent. Okay. So why is that clear? If you're Cauchy, then you're bounded. Why should that be like, oh yeah, that makes a lot of sense. If you're Cauchy, remember what Cauchy means, right? Cauchy means that the diameter of the tail goes to 0, right? The diameter of the tail goes to 0. Well, choose the point past which the diameter of the tail is 1. Okay, that means that from some point onwards, everybody lies within a unit ball, right? I mean, a ball of diameter 1. Okay. Right? And then there's a bunch of guys before. Maybe there are 10 billion guys before, but it's still some finite number, right? Well, those 10 billion guys, you bound them because they're finite, right? So you got these guys. The guys before are bounded by taking some large distance, right? And the guys after, the infinite tail is bounded by is controlled in this little ball, in this little disk, right? So Cauchy implies bounded. Okay. So that's the idea. Yeah. So, and in fact, so this is exactly what I wrote here. So if P sub n is Cauchy, then we know that for some n, the diameter of P sub n, the tail, is smaller than 1, right? Then since P sub n is just P sub 1 to P sub n minus 1, union the tail, we have that P sub n is bounded, right? Because you can find you can find some ball that contains this guy, and you have a ball that contains this guy. Okay, Max.
Why can't that same reasoning be applied to spaces that are not Euclidean? Like what part of the proof falls apart?
Well, the boundedness part, right? It's not true that boundedness implies. It's not true that closed and bounded implies compact. Yeah. So that for that we needed the Heine-Burrell theorem. Okay. Okay. So just one more small thing about convergent sequences. Convergent sequences are bounded. Are bounded sequences convergent? Are bounded sequences convergent? No, right? Of course not, right? You could take P sub n being -1 to the n, right? That's a bounded sequence, right? But it doesn't converge. Okay. However, there is one type of sequence for which convergence and boundedness are the same, are equivalent, and these are the so-called monotonic sequences. Okay, so monotonic sequences. Okay, so you have some sequence in Rn. I'm sorry, in R, not in Rn. If S of n, if S of n plus 1 is always bigger than or equal to S of n, we call it, for all n, we say that S of n is monotonically increasing. Okay, and similarly, we're decreasing. And there's a theorem that comes in handy every once in a while called the Monotonic Sequence Theorem. And that is if S of n is a monotonic sequence, then Sn converges if and only if Sn is bounded. Okay. For monotonic sequences, convergence and boundedness are equivalent to. Okay. So we already know that convergence implies bounded. Right? Convergence implies boundedness. That I think we've shown before, so we don't need to. That we don't have to worry about. The only thing we need to show is that bounded implies convergent. Okay. For a monotonic sequence, bounded implies convergent. And what you do is you say, well, let's, without loss of generality, assume that S of n is increasing. Right? A similar proof will work for decreasing. So, so let E sub 1 be the set of all outputs. Okay. Let E sub 1 be the set of all outputs. So if you want, here's your time. You've got this monotonically increasing sequence, right? And you take all the outputs, and these guys are E sub 1. Okay. Take all the outputs, and those guys are E sub 1. Okay. So the set of all outputs of your sequence. We know E sub 1 is bounded above, right? Because the sequence is bounded. Right. So we know that there's some upper bound for the set. Okay, so who can tell me why the sequence has to converge? Why must the sequence converge? Well, first off, what do you think it's going to converge to?
If
Well, m could be much bigger. So these guys might be down here, and m is some huge number. So not m, but the supremum. Yeah. So right. E1 is bounded above, so there exists a supremum, right, a least upper bound of E, right? Least upper bound of E1. Let's call that thing, I don't know, L. Okay. And we claim that then the sequence S of n converges to L. The sequence converges to L. Okay. Why is that true? Well, pick any epsilon. Right? Pick any epsilon. So here's let's say that this is our L. Okay. Pick any epsilon, and we know there must be somebody. There exists some piece of n in L minus epsilon. Actually, let me write it like this. Why am I writing it that way? I've written it backwards. It's written it backwards. Sorry. L minus epsilon L. Right. There's got to be somebody in there. Otherwise, this isn't an upper bound. Right.
Why didn't you close the left side?
Isn't it like puncture or something?
So remember this guy is the least upper bound, right?
Oh.
This guy's the least upper bound. All I'm trying to say is that there's got to be somebody inside here, right? Because if there were not anybody in here, then if there were not any of the, right? So here I look at L minus epsilon. If there's nobody in here, this is not the least upper bound, right? I can take a lower thing, and that would be the least up. That would be also an upper bound. Right?
But L doesn't have to be in there, right? The supremum doesn't have to be in there.
So.
Because that implies that Pn could be L, but that's not necessarily true.
I'm trying to exclude the possibility of Pn being L, right? So
But then,
it's true that, so L is the supremo. It could be that Pn actually is just L, right? That from some point the sequence jumps up to L and just stays there. L, 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 L,
but then it exists. It doesn't change
right?
identity.
In that case, I'd run into trouble here. So I'm excluding that possibility. Okay. So in any case, this is true, right? You guys don't worry about anything except for this statement here, right? There exists some Pn in this half-closed neighborhood, right? Because otherwise, L is not the upper bound, right? Is that convincing?
Yeah.
It should be, I hope. Right?
Yeah.
There's nobody in there. I mean, there's got to be somebody in there. Okay. But then, since this is an increasing sequence and this is an upper bound, we know that everybody lies inside there, right? Then, actually, let me call it P sub capital N. Then, since P sub N is increasing, and L is an upper bound, L is an upper bound of E1, we have that n bigger than n implies that P sub n lies in L minus epsilon comma L. Okay, right? That is, we found an n such that n bigger than n implies P sub n lies in the epsilon neighborhood of L, right? Because we lie in the half epsilon neighborhood, we certainly lie in the whole epsilon neighborhood, right? We've found a time, we know that past some time n, everybody lies inside of here. Well, then we lie inside of this full epsilon neighborhood, right? And that's what you need to show for convergence, right? You need to show that given some epsilon neighborhood, there's a time past which everybody lies inside the epsilon neighborhood. Mint.
Is there a reason why you don't use Sn and use Pn instead?
I'm sorry. These P's should all be S's. I'm sorry. Yeah. These are all S's. The reason is that I'm losing my brain. You laugh, but it's true. Yeah, learn as much as you can while you're young before your brain starts to deteriorate. Yeah, don't waste your time making friends or dating. Just learn. Okay, any questions about the math? Any questions about this? Okay, it's pretty straightforward. Okay, so now we're going to get on to something that that nobody likes, maybe, but is really useful. So lim inf, lim sup. The limit inferior, the limit superior. So this is sort of like a refinement of the notion of limit. Right? The limit inferior and the limit superior. Okay. So so first off, it'll be useful for us to have the following notation that we say a sequence converges to positive infinity if, given any m, there exists a time such that past that time Sn is bigger than m. Right, so you've got this sequence. Okay, and no matter what height you give it, there's a time past which it's above, everybody's above that height, right? So no matter what bar you give it, there's a time past which everything will exceed that bar. Okay, if that happens, we say the limit is infinite, right? And you can imagine we do the opposite, right? We say, if we reverse this, then we say the limit is negative infinity. Okay. Okay, so here's the definition of lim sup. You've got a sequence of real numbers. And you let E, which is in the extended reals. Okay, so let E, a subset of the extended real numbers, denote the set of all subsequential limits of S of n. Okay, by that I mean you take all possible subsequences and look to see what limits those guys have, and that's your set. Okay. Okay. So you look at all possible limits of subsequences. Right. Right. In other words, it's all x such that S and k converges to x for some subsequence. For some subsequence S and k of Sn. Okay. We define the lim sup of your sequence as the supremum of this set. Okay. The supremum of the set of subsequential limits. Okay. It's also denoted lim with a bar over it. Okay. And then lim inf, as you might guess, is going to be the infimum and denoted with a bar below it. So just to give a simple example, right? If my Sn is -1 to the n, right? So I've got this sequence, it just bounces back and forth, -1, 1, -1, 1, -1, 1, -1, 1, right? Okay, and I look at the subsequential limits. Well, what are my subsequential limits? There's only two possible limits for my subsequences, 1 and -1, right? Right. I can make the sequence 1, 1, 1, 1, 1. That has a limit of 1. I can make the sequence -1, -1, -1. That one has a limit of -1. Right. Those are two of my subsequential limits, and I can't really get anything else other than that. Right. Okay. So the lim sup of this thing is 1. The lim inf of this thing is -1. Okay. Question?
If Sn converges, is lim inf equal to lim sup?
Yes. Yes. Right, because somebody explained it to me. Why is that true? If you have a convergent sequence, then what do you know about your subsequences?
They're all going to have the same limit.
They all converge to that limit, right? So what's the set of subsequential limits? That's 1 point, right? It's 1 point. Well, the lim sup of that is that point. The lim inf of that is that point, right? Yeah, and the converse is also true, but we'll get to that. Okay, so let me give another example. Let's suppose that my sequence S of n looks like this: 1/2, 1/3, 2/3, 1/4, 2/4, 3/4, 1/5, 2/5, 3/5, etc., etc. Okay. Talk to each other and tell me what. Talk to your neighbor and talk about the lim sup and the lim inf. Okay, who wants to say? Right. What's the lim inf? Lim sup? 1, right? 1. Right? Because you can make some subsequence that go. Clearly, you're not going to get anything more than 1. Right? All these guys are between 0 and 1. Right? Right. So, and you can see that you can construct a sequence that converges to 1. Right? You could, for example, you could take these guys. These guys only, and that sequence would converge to 1. And what's the lim inf?
0.
It'll be 0, right? Because you can take these guys, 1/2, 1/3, 1/4, 1/5, blah blah blah, and those guys would converge to 0, right? And those are, pretty clearly, the biggest and smallest subsequential limits that you can get.
For the sequence that converges to 1, can you also take 1/2? I think
Yeah.
you can, right?
Yeah. I mean, you could start off with, you could, as long as you make some sequence that converges to, that converges to 1, then it's okay. We can throw in a bunch of other guys, as long as in the end it converges to 1. Right. What is the set of subsequential limits of this sequence? You just told me about the supremum and the infimum of that set. What is the actual set?
The set of rational set of rational numbers from 0 to 1.
Almost. The set of reals from 0 to 1, yeah, inclusive. Maybe I should put that in the homework, just so that you have to write it out. But, okay, so we got 10 minutes. That should be enough time, I hope, to do the following theorem, which is very useful. This is a characterization of the lim sup. Okay. So S of n, a sequence in R, E as above, right, the set of subsequential limits. Then the lim sup of the S of n is in E. The lim sup is itself a subsequential limit. As it was in our example over here, right? The lim sup turned out to be one of the subsequential limits. And for any x bigger than lim sup, there exists an n such that if you're past that n, then all Sn are smaller than x. Okay, I think it might be nicer to write it this way, right? Given any epsilon, there exists an n such that if you're past that n, then S of n is smaller than lim sup plus epsilon. Yeah, Dave.
Can you say something stronger, like E is closed?
Yes. Yes, that's actually part of the, that would be part of the proof. We'll use that to prove this. Yeah. I'm just going to have you do that as an exercise. Okay, so, okay, so, and there's a further part, further, any number satisfying 1 and 2 nice to say, the only number satisfying 1 and 2 is the lim sup. So if you have a subsequential limit with this property, it's got to be the lim sup. Okay, so this is another way of describing the lim sup, right? It is one of the subsequential limits that has this upper bound property. Yeah, Aria.
Can you say the same thing, just like swapping things and flipping things for the lim inf?
Yeah, the lim inf is going to be an element, and it's also going to have this property that for any epsilon, there's a time past which everybody is above that thing minus epsilon. Okay, so yeah, this is actually really useful. The way you want to think about it is, so say this guy is the lim sup. Okay. Suppose this guy is the lim sup, but let's focus on property number 2, because that's kind of a useful one. If this guy is the lim sup, what that says is that given any epsilon, right, so lim sup plus epsilon, given any epsilon, there's a time past which everybody is below that line. Okay, it might be well below that line. Okay, right, but everybody's below that line. Okay, so you can control the upwards behavior of your sequence. Okay, but you cannot control the downwards behavior of your sequence with the lim sup. Okay, now the lim inf does the opposite, right? The lim inf says, well, if this guy is my lim inf, then given any epsilon, there's a time past which everybody's above that lower bar, right? And it could be, well above that lower bar. Okay. Okay. So what if the lim sup and the lim inf are the same? What if the lim sup and the lim inf are the same? That would mean that given an epsilon above, you can find somebody, a time past which everybody's below that bar, and given a time below, given a epsilon below, you can find a time past which everybody's above that. So what does that tell you? That tells you that that is, so you find a time past which everybody's in the epsilon neighborhood, and thus that number, the lim sup and lim inf, is the, somebody said it?
Limit.
The limit, right? The limit, right? Right? Because that's what a limit is, right? That you can control it above and below, right? Lim sup allows you to control the above. Lim inf allows you to control the below. If you have control both above and below, then you must be the limit, right? So if the lim sup equals the lim inf, then that number is the limit. Okay. About 3 minutes. I was wrong. We would not be able to finish this. Let's prove a fact that we're going to need along the way. So here's a lemma that the set of subsequential limits of a sequence K sub n in a metric space X form a closed subset. Form a closed set, sorry. Okay. So you have some sequence, right? You have some sequence. Here's your timer, right? Here's your metric space. You have some sequence, right? And you've got subsequential limits. Okay. And you want to say that any limit point of this set, right? So so let E star denote the set of subsequential limits. Right? And let Q lie in E star prime. Okay. So Q is a limit point of the set of subsequential limits. Right? Right? That means that every punctured neighborhood of Q contains a subsequential limit. Right. Every punctured neighborhood of Q contains a subsequential limit. So here's Q. There's going to be some subsequential limit in there. Okay. And our claim is that Q is a subsequential limit. Right? Q is a subsequential limit itself. Okay. So, while you think about that, you say, well, look, if I take an epsilon here, let's take an epsilon of 1, say. Okay. I know that, let's say, in the half neighborhood, there's going to be a subsequential limit inside there, right? Because this guy is every neighborhood contains a subsequential limit. I know that there's going to be some subsequential limit inside there. Okay. So then, that guy is the subsequential limit of my sequence, right? Of my sequence P sub n. So inside that guy's half neighborhood, inside that guy's half neighborhood, there must be some P sub n, right? There must be some P sub n sub 1 inside there, right? Okay, so that will be my first. I'm trying to make a sequence of P sub n's that converge to Q. This is my first one. And you can guess what I'm going to do next, right? I'm going to take, what I do next is I look at Q again, and this time I start with a radius of 1, and I take the half neighborhood, and I know that inside there is another E star, right? There's going to be inside there some E2 star. Let's call this guy E1 star, right? And I know inside that guy's half neighborhood, there's got to be somebody, there's got to be a P sub n2, where n2 is bigger than n1, right? Because it's an infinite sequence, so eventually it's going to get, those indices are going to get bigger than n1. So I can choose somebody inside there, and so on and so forth, right? I keep on going inductively in this manner, and I get a sequence that converges to Q, and thus Q is itself a subsequential limit. Okay, so anybody, so the set of subsequential limits is a closed set. Right? Any limit point is itself a subsequential limit. Okay, I'll write this up more formally next time. Let's stop here for today.